All right, let's jump right in. Today we're going to tackle one of the biggest, most fascinating challenges in all of psychology, trying to figure out the inner workings of the human mind. I mean, we can't just pop the hood and take a look inside, right? So how in the world do we map its hidden architecture?
And that really is the million-dollar question, isn't it? Answering this is what takes psychology from just, observing what people do and pushes it into the realm of a truly predictive science. We're trying to move beyond just describing behavior to actually understanding the how and the why behind our thoughts. For the longest time, this has been the central problem. We can see an input, like, say, a tricky question on an exam, and we can see the output, the answer someone gives. But that whole complex, mysterious chain of events that happens in between, that's all happening inside the black box. So how do we possibly map something we can't see? Well, the solution is, we draw its blueprints. And no, not with pencils and paper, but with the clear, powerful, and precise language of mathematics. This is what lets us build concrete, testable models of how the mind might actually be structured.
Okay, so let's really dive into this. We're going to explore how we use these mathematical blueprints to take our theories about the mind and make them solid, concrete, and something we can actually test. First up, let's look at how these models can map what we know. We'll start with something that feels almost impossible to map, knowledge itself. I mean, how can you possibly create a structured blueprint for what a person knows, or maybe more importantly, what they don't know? Well, one of the main tools we use for this are these things called cognitive diagnosis models. The idea here is, instead of just giving a student a single score on a test, these models dig deeper. They look at the pattern of their answers to figure out which specific underlying skills they've truly mastered. Okay, take a look at this. This is a Q matrix, and it's really the heart of how these models work. Think of it like a blueprint for an exam that experts create before a single student takes it. It breaks down exactly which skills are needed for each question. So you can see question 1 needs you to add fractions and find a common denominator, but not simplify. Question 3, on the other hand, needs all 3 skills. The model then uses this map to make sense of a student's answers. And this is where it gets really powerful. By checking a student's right and wrong answers against that Q matrix, the model can infer their unique skill profile. It doesn't just tell a teacher the student is bad at math. It might say, hey, this student has mastered adding in common denominators, but they're really struggling with simplifying fractions. That allows for incredibly targeted, personalized help. It's a real game changer for education. All right, so that's a model for knowledge. Now let's switch gears and look at the architecture of sight. How do we build a model of that incredible, hidden processing that makes our visual world seem so effortless? I mean, this is the core puzzle of perception. Think about it. Right now, your eyes are being bombarded by a chaotic flood of light, color, and shadow. So how does your brain take all that noise and magically organize it into the stable, coherent world you're seeing in front of you?
A big piece of that puzzle is something called perceptual grouping. You probably remember the Gestalt principles from your intro psych class, our brain's automatic habit of grouping things by proximity, seeing continuous lines, filling in the gaps. Well, what mathematical models do is they take these cool-sounding principles and turn them into precise computational rules that can actually predict how someone will structure what they see.
The way modern models do this is by formalizing the process, kind of building a picture from the ground up. They specify how our visual system takes these little low-level primitives, basic stuff like edges, textures, and colors, and combines all those signals, weighing the different cues, to form one stable, global perception of the world. Okay, we've seen models for what we know and what we see. Now let's try to map the very architecture of judgment itself. How do we structure our choices? So a lot of you have probably come across this idea of 2 systems of thinking, right? You've got system 1, which is your fast, intuitive, gut-feeling mode, and then you have system 2, the slow, deliberate, analytical one. Well, what bounded rationality models do is put some math behind that idea. They treat the mind like an information processor that has to decide when to use a low-effort shortcut and when it needs to fire up the expensive analytical system, especially when it runs into something new or unusual. Here's another really cool approach: stochastic network models. The idea here is to take a complex task, like, say, deciding if you recognize a face, and break it down into a whole network of simpler little sub-processes. Is it a face? Is it male or female? Do I recognize the eyes? By mapping out how all these little steps are arranged and how our attention is divided, these models can make incredibly specific predictions about things like your reaction time. So,
We've seen a few examples of what these models can do, but how do researchers actually build them? Let's take a peek inside the mathematician's toolkit.
A massive one in modern cognitive science is Bayesian inference. Now, the basic idea here is to think of the mind not as a perfect logic machine, but more like a probability machine. It assumes that we all walk around with some prior beliefs about how the world works, and as we get new evidence from our senses, we constantly and pretty optimally update those beliefs. It's a super powerful way to model how we learn and see in a world that's full of uncertainty.
Another essential tool comes from a field you might not expect: information theory. This was originally developed for things like telephone communications, but it gives us a mathematical way to quantify information itself. This lets cognitive scientists analyze how efficient our mental processes are and understand the hard limits on our brain's ability to process information, almost like figuring out the bandwidth of our own internal internet connection.
Which of course brings us to the big picture question. Why go to all this trouble? Why bother translating our psychological theories into all this complicated math? What's the real payoff? Well, the benefits are just huge. First, math forces you to be precise. You can't really be vague in an equation. That precision leads directly to testability. The models spit out hard numbers, like a predicted reaction time of exactly 540 milliseconds that we can actually go out and test. And that's what moves psychology from just describing behavior to actually predicting it. Finally, it gives us a systematic way to compare different theories and see which blueprint actually fits the data best. The psychologist James E. Cutting really hits the nail on the head here. This whole approach changes how we even judge our theories. It's not just about finding the simplest or most accurate model anymore. It's about finding the most flexible one, a blueprint that we can adapt and improve as we learn more about the incredible complexity of the mind.
So, here's the bottom line. The crucial takeaway is this: these mathematical blueprints are way more than just a fancy academic exercise. They are the tools that are fundamentally transforming cognitive psychology. They let us crack open that black box, not by physically looking inside, but by drawing a map so precise it can start to predict the mind's behavior before it even happens. And that leaves us with a final, kind of mind-bending thought. As these tools get even more sophisticated and our data gets richer, what parts of our human experience that seem totally mysterious today? I'm talking about things like creativity, insight, maybe even consciousness itself. What if they one day have their own blueprints? What if they move from the realm of philosophy into the world of predictive science? Thanks for joining me.